name is Sonika. I'm a student of BSc Chemistry Honors, second year. I'm going to read the chapter Diazonium Salts. Introduction. Arene diazonium salts were discovered by John Peter Grace in 1858. They have the general formula ArN2 positive X, where Ar stands for aryl group, X stands for any anion such as chloride, bromide, nitrate, HSO4 negative, BF4 negative, etc. Aliphatic diazonium salts are also known, but they are highly unstable. They rapidly decompose even at low temperature, forming carbocation and nitrogen gas. Rn N positive triple bond NX negative, R positive carbocation plus N2 plus X negative. Therefore, in this unit, we shall discuss the chemistry and synthetic application of arene diazonium salts, only particularly with reference to benzene diazonium chloride. Nomenclature. Diazonium salts are named by adding the suffix diazonium to the name of an aromatic compound, followed by the name of anion. For example, benzene diazonium chloride, para-toluene diazonium hydrogen sulfate, para-nitrobenzene diazonium fluoroborate, para-chlorobenzene diazonium bromide. Structure of benzene diazonium chloride. First is molecular formula. The molecular formula of benzene diazonium chloride is determined from analytical data and molecular weight determination is C6H5N2Cl. Second is Gray's structure. Gray's proposed structure 1 for benzene diazonium chloride, in which both the nitrogen atoms were directly linked to the benzene nucleons. Its salt-like character, displacement of both the nitrogen by univalent atom or group in most of its reaction, its reduction to benzene hydrazine, in which only one nitrogen is attached to benzene ring, formation of azo compounds by coupling reaction, formation of aromatic diazonium salt from penta-substituted aniline. Kekulé structure. Kekulé proposed structure for benzene diazonium chloride, in which only one nitrogen was linked to the benzene nucleus. Evidence in favor. Structure to explain most of the drawbacks of Gray's structure 1, such as its reduction to phenylhydrazine, formation of azo compounds by coupling reaction, preparation of diazonium salt from penta-substituted anilines, and displacement of both the nitrogen atom by univalent atom or group. Points against Kekulé structure. Structure 2 cannot explain its salt-like character, its instability as compared to azo compound, since both contain N double bond N linkage. Bloom strand structure, that is fourth. Bloom strand suggested structure 3 for the benzene diazonium chloride, in which the nitrogen attached to the benzene ring is pentavalent while the other is trivalent. Evidence in support. It explains all the objection of structure 1 and 2. Structure 3 is further supported by the following fact. First, its readily solubility in water but not in common organic solvent. Second, its complete ionization as shown by conductivity measurement. Third, the presence of triple bond as shown by infrared spectroscopy. Fourth, its instability as compared to azo compounds. Fifth, it explains the geometrical isomerism as shown by diazotates or diazotates, which are metallic salt of diazonium hydroxide. Benzene diazonium chloride. It converts in presence of NaOH or HCl, benzene diazonium hydroxide. Sodium benzene diazide in presence of NaOH and HCl converts into benzene diazohydroxide. The sodium benzene diazotate can exist as a pair of geometrical isomers due to hindered rotation about the N bond. Preparation of diazonium salt. Aromatic diazonium salt are generally prepared by adding a cold aqueous solution of sodium nitrite to the solution or suspension of primary aromatic amine in an acid at 273 to 278 Kelvin. ArNH2 plus NaNO2 plus 2 mole of HX 273 to 78 Kelvin. Arene diazonium salt plus NaX plus 2 mole of H2. For example, C6H5NH2 plus NaNO2 plus 2HCl 273 to 78 Kelvin. Benzene diazonium chloride plus NaCl plus 2 mole of water. Diazonium salt are also formed when aromatic primary amine react with nitrite acid such as amyl nitrite. The nitrite esters needed for the purpose are prepared by the treatment of alcohols with nitrous acid, thus C5H11OH amyl alcohol plus nitrite. It converts into amyl nitrite water. Then amyl nitrite react with HCl and C6H5NH2 273 to 78 Kelvin benzene diazonium chloride amyl alcohol plus water. The process of conversion of primary aromatic amine into diazonium salt is called diazotization. General procedure for diazotization. The primary aromatic amine is dissolved or suspended into dilute acids such as HCl, H2SO4, etc. 3 moles of the acid are generally used for every mole of the amine which is to be diazotized. 1 mole to form the salt of the amine, 1 mole to form the liberate nitrous acid, 1 mole from sodium nitrite, 1 mole to keep the reaction mixture acidic, enough to suppress the undesirable side reaction such as coupling of diazonium salt, thus formed with free amine. The amine solution is cooled and cold aqueous solution of sodium nitrite is added slowly to it at such a rate that the temperature of the cold aqueous solution of reaction mixture does not rise above 278 Kelvin. The addition of sodium nitrite solution is stopped as soon as few drops of the reaction mixture produces a blue color with starch potassium iodide paper showing the presence of unreacted nitrous acid in the reaction mixture. The addition of the sodium nitrite is generally avoided. It subsequently interferes with the reactions of diazonium salt. The excess of nitrous acid may be destroyed by the addition of urea, NH2CONH2 plus 2HONO, 2 moles of N2CO2 plus 3H2. Since diazonium salt decomposes even at low temperature, 273 to 278 Kelvin, they are used immediately after preparation. Evidence and support. The mechanism is supported by the observation that aromatic amines containing electron withdrawing groups such as NO2 are less easy to diazotize. This is due to the reason that the nucleophility of the amino group is reduced due to the electron withdrawing effect of NO2 group as shown below. Such amines be diazotized in acidic medium. Conversely, aromatic amines containing electron donating group such as at ortho position or para position, ortho-tolidine, para-anisine undergo diazotization much more readily than aniline. Stability of diazonium salt. Aromatic diazonium salt are much more stable than aliphatic diazonium salt due to the dispersal of positive charge over the benzene ring. The instability of the diazonium salt is due to their tendency to eliminate an exceptionally stable molecule of nitrogen to form the carbocation. Since the phenyl carbocation is much less stable than alkyl carbocation, aromatic diazonium salt have much lower tendency to eliminate nitrogen than aliphatic diazonium salt. In other words, aromatic diazonium salt are much more stable than aliphatic diazonium salt. Physical properties: aromatic diazonium salts are generally colorless crystalline solid, highly soluble in water. Many diazonium salts, especially nitrites, are dangerously explosive in the dry state. Therefore, they never isolated, but are usually prepared in situ and used extensively after preparation. However, certain diazonium salts, such as fluoroburyates, are relatively insoluble in water and are stable enough to be dried and stored. Some diazonium salts also form complexes with metallic salts such as zinc chloride, Rn2 positive, ZnCl4 2 negative. These complexes are generally insoluble. Chemical properties: arene diazonium salts are highly reactive compounds. Their high reactivity arises due to excellent leaving ability of the diazogroup as nitrogen gas. They are therefore extremely useful synthetic reagents in organic chemistry. The reaction of diazonium salt are broadly divided into two categories. A. Reactions in which the diazo group is replaced by monovalent atoms or group. Second is the reaction in which the nitrogen atom are retained. Reaction in which the diazo group is replaced by a monovalent atom or group. Some important reactions of this category along with their synthetic application are discussed below. First is replacement by hydrogen deamination. The replacement of diazo group by hydrogen and reduction of diazonium salt to arenes, their hydrocarbons, is usually brought about by treating a diazonium salt with hypophosphorus acid at room temperature, preferably in presence of Cu1 salt as catalyst. This reaction can be carried out by treating amines with sodium nitrite and hypophosphorus acid as diazotizing agent. Diazo group may be replaced by hydrogen by heating arene diazonium salt with ethanol. The whole process involving the diazotization of an amine followed by reduction of diazonium salt or replacement of diazo group by hydrogen is called deamination. It may be emphasized here that during the reaction of diazonium salt with ethanol, two products are usually obtained. One involving the replacement of diazo group by hydrogen as discussed above, and the other by the ethoxy group. The relative amount of two products, however, depend upon the nature of diazo compound in alcohol used. If a I group is present in the nucleus, ethanol is used. The replacement of diazo group by hydrogen predominate. If on the other hand methanol is used, the predominant product is aryl methyl ether, that is anisole. Synthetic implication: the importance of deamination is illustrated by the following application. First is the synthesis of metapromotolene. Metapromotolene cannot be prepared by direct bromination of toluene or Friedel-Crafts alkylation or bromobenzene due to ortho para-directing nature of the methyl group. Second is the synthesis of 1,3,5-dibromobenzene or symmetrical tribromobenzene. Third is the synthesis of 3,5-dibromotoluene. Recall: direct bromination of toluene with Br2 FeBr3 gives 2,4-dibromotoluene. Replacement by hydroxyl group. Synthesis of phenol. Diazonium salt react with water in presence of acid to form phenol. The reaction is generally carried out by adding the solution of a diazonium salt to a large volume of boiling dilute sulfuric acid. For example, benzene diazonium chloride plus water which is boiling in presence of H2SO4. Phenol is prepared and nitrogen gas is released plus HX. The acidic condition minimizes the side reaction involving the coupling of phenol with diazonium salt. Synthetic application. This reaction is especially important since only a few methods are available for direct introduction of hydroxyl group into benzene nucleus. Synthesis of metanitrophenol. Replacement by halogen, that is third. Different methods are used depending upon the type of halogen to be introduced. First is the replacement by chlorine or bromine. Sandmeyer reaction. Aryl chloride and bromide can be easily prepared by treating a fleshy prepared cold aqueous solution of an arene diazonium salt with a solution of cuprous chloride in hydrochloric acid or cuprous bromide in hydrochromic acid. This reaction is called Sandmeyer reaction and gives aryl halide in 60 to 80% each. Benzene diazonium halide in presence of CuBr and HBr. It gives aryl bromide plus nitrogen gas plus X negative. In presence of CuClHCl, it gives benzene chloride plus nitrogen gas plus halide ion. It may be noted that it is the halogen which is attached to the copper which enters the nucleus. Mechanism of Sandmeyer reaction is believed to occur by free radical pathway. Ketemen reaction. It is the modification of Sandmeyer reaction in which copper powder and a hydrogen halide are used instead of cuprous halide dissolved in the corresponding hydrogen halide. ARBR from benzene diazonium chloride halide in presence of CuHBr. Benzene diazonium halide in presence of CuHCl gives benzene diazonium chloride. Yield are often lower, around 40% than those obtained by Sandmeyer reaction. Synthetic application, that is synthesis of 1,2,3 tribromobenzene. Now B part, which is replacement by iodine. The replacement of diazo group by iodine does not require cuprous halide or copper as a catalyst. It is simply achieved by treating a diazonium salt with potassium iodide. Now synthesis of para-nitrobenzene. C is the replacement by fluorine. Ball-Schiemann reaction. When an aqueous solution of diazonium salt is treated with fluorophoric acid HBF, diazonium fluoroborate gets precipitated. It is filtered and dried. Unlike other diazonium salt, diazonium fluoroborates are fairly soluble stable compounds. When dried diazonium fluoroborate is heated, it decomposes to produce aryl fluoride and boron trifluoride. For example, benzene diazonium chloride plus HbF4, it gives diazonium fluoroborate, and when it is heated, it gives aryl fluoride plus boron trifluoride. Mechanism. The reaction occurs by SN1 mechanism as shown below. Synthetic application, that is the synthesis of fluorobenzene. Fourth is the replacement by the cyano group. Synthesis of nitrile. Aryl nitriles can be prepared by treating a diazonium salt with cuprous cyanide or potassium cyanide and copper powder to avoid the loss of cyanide as ethane. The diazonium salt solution is first neutralized with sodium carbonate and then treated with cuprous cyanide. This reaction is called modified Sandmeyer reaction. Synthetic applications. Since hydrolysis of nitrile gives carboxylic acid, if the synthesis of nitrile provides us with an excellent method Preparation of carboxylic acid from nitro compound. For example, that is from toluene we formed paratolic acid, replacement by the nitro group. Fifth, nitro compounds are generally prepared by treating and benzene diazonium fluoroborate with an aqueous solution of sodium nitrite in presence of copper powder. We take benzene diazonium chloride, addition of HBFO, it gives benzene diazonium fluoroborate, NaNO2 Cu presence nitrobenzene plus nitrogen gas plus NaBFO. Now, sixth is the replacement by an arsenic acid, ASO3H2 group, that is part reaction. Treatment of ferrine diazonium salt with sodium arsenide in presence of copper sulfate followed by acidification gives an aryl arsenic acid. For example, benzene diazonium chloride plus Na3ASO3 in presence of CuSO4 is C6H5ASO3 Na2 plus NaCl plus N2. And now C6H5ASO3 Na2 in presence of 2 mole of HCl, it gives phenyl arsenic acid C6H5ASO3 H2 plus 2 mole of NaCl. Seventh is replacement by an aryl group, that is Gomberg-Bachmann reaction. When an arene diazonium salt is treated with an aromatic compound, liquid or its solution, or in an inert solution if solid, in presence of an aqueous alkali, biaryls are formed. Yields are usually less than 40%. Benzene diazonium halide plus benzene NaOH-ArC6H5 plus HCl plus N2. For example, we take 4-bromo benzene diazonium chloride C6H6 NaOH. It gives para-bromo diphenyl plus nitrogen gas plus HCl. Now, mechanism. The reaction is believed to occur by free radical mechanism in alkaline medium. Diazonium salts are converted into corresponding azo compound which decompose to produce aryl radicals. B. Reaction in which nitrogen is retained. First reaction in which nitrogen is retained is reduction to aryl hydrogens. Arene diazonium salt upon reduction gives good yield of aryl hydrogens. This reduction can be brought about by number of reagents such as stannous chloride, hydrochloric acid, sodium sulfite, sodium hydrosulfite, and even electrolytically. We take benzene diazonium chloride in presence of SnCl2HCl or Na2SO3, we get phenylhydrazine. If, however, strong reducing agent such as ZnHCl is used, the product is an aromatic amine. Benzene diazonium chloride in presence of zinc and HCl, it gives phenylhydrazine. In presence of zinc and HCl, it further gives aniline plus ammonia. Mechanism of reaction of diazonium salt with sodium sulfite. Reaction probably occurs through nucleophilic attack by the sulfur atom of the sulfide ion on both the nitrogen atoms, forming the dianions of hydrazine sulfonic acid, which is then converted into hydrazine in presence of acid. Now, second is the coupling reaction. Arene diazonium salt react with highly reactive electron-rich aromatic compounds such as phenol and amines to form brightly colored azo compound ARN double bond N ER. This reaction is known as coupling reaction and it is extensively used in azo dye industry, whereas coupling with phenol occurs in basic medium pH 9 to 10 and that of amines occur in purely acidic medium pH 4 to 5 at 273 to 278 Kelvin. Benzene diazonium chloride is phenol in presence of OH negative pH 9 to 10, 273 to 278 Kelvin, we get para-hydroxybenzene orange colored plus HCl, benzene disonium chloride plus aniline in presence of H positive pH H4 to 5, 273 Kelvin to 278 Kelvin, we get diazoaminobenzene. On further rearrangement, H positive, we get para-aminoazobenzene, which is yellow in color. Coupling usually occurs at para position with respect to OH or the NH2 group. If, however, the para position is blocked, it occurs at the ortho position. For example, benzene disonium chloride paracrysol OH negative in presence of pH 9 to 10, we get 2-phenyl iso 4-methylphenol. If the compound contains both amino group as well as hydroxyl group at para position with respect to each other, then the orientation of coupling reaction can be changed by changing the pH of the medium. For example, we have para-aminophenol in presence of benzene disonium chloride OH negative pH 9 to 10. We get 4-amino-2-phenyl azophenol plus HCl in presence of para-aminophenol and benzene disonium chloride H positive pH 4 to 5. We get 4-amino 3-phenyl azophenol plus HCl. The well-known indicator methyl orange, which is widely used in acid-base titration, is obtained by the coupling of diazonium salt of sulfanilic acid with N,N-dimethyl aniline. Sodium salt of sulfanilic acid in presence of Na2 NO2 HCl. We get N,N-dimethyl aniline, and we also obtained pH 4 to 5 methyl orange. Mechanism of coupling reaction. The coupling reaction between benzene disonium chloride and phenols or amine is an example of electrophilic substitution reaction in which the disonium ions act as the electrophile while phenol or amine act as the nucleophile. A. Coupling with phenol. Since benzene disonium ions are only weakly electrophilic, therefore strong nucleophiles are needed for the reaction to occur. Whether since phenol is weakly nucleophilic to the phenoxide ion is strongly nucleophilic, therefore coupling reaction of phenol are usually carried out in alkaline medium. Benzene disonium chloride. It forms para-hydroxyazobenzene. Role of pH. The pH of the medium plays an important role in the coupling of phenol as stated above. That the coupling of the phenol is carried out in the weakly basic medium as explained above. In the alkali medium, the diazonium salt first forms diazonium hydroxide, which immediately rearranges to form diazohydroxide, which further react with alkali to form corresponding salt called the diazotate. All these three species in fact exist in equilibrium as shown below. Benzene disonium chloride OH positive gives diazonium hydroxide, couples, rearranges diazohydroxide and does not couple, and it gives sodium diazotate. Since at high concentration of OH negative ions, equilibrium will shift in favor of diazohydroxide and diazotate, both of which do not couple. Therefore, for the desired coupling reaction to occur, the pH must be kept as low as possible in the alkaline medium. However, a too low pH would suppress the dissociation of phenol to phenoxide ion. Phenol in presence of OH negative and H positive gives phenoxide ions couples quickly. Therefore, to carry out the coupling reaction, an optimum pH is needed. In actual practice, the optimum pH for such coupling reaction is between 9 to 10. B. Coupling with amines. Tertiary amines. The mechanism of coupling reaction of diazonium salt with tertiary amines is similar to that of phenol, except that the coupling is carried out under weakly acidic conditions. C is the reaction with primary and secondary amines. Coupling of diazonium salt with primary or secondary amines occur in neutral or mildly alkaline medium, where NH2 group of the amine first attacked the diazonium cation to form diazoaminobenzene. However, when the diazoaminobenzene thus form is heated in presence of acidic medium, it undergoes diazoaminoazo rearrangement to form para-aminoazobenzene by the following mechanism. Role of the page. In presence of high concentration of H positive ions, the lone pair of electron on the N atom except of proton. As a result, the amines exhibit predominantly in the protonated form. Due to the absence of lone pair of electron on the nitrogen atom, the amine is no longer nucleophilic. Thank you.